Hello. So I just wanted to make a quick note about the second fundamental form based on my lecture one recap review video. So we're probably going to get into the second fundamental form more in detail later, but I just wanted to mention that we were looking at a fixed embedding of a Euclidean space or an open subset of Euclidean space Rn into a larger ambient space R capital N, let's say. And we supposed that we had a fixed embedding, and the image of this embedding we're thinking of as like a piece of a manifold. So in this setting, which is the Euclidean setting, and I will note with the Euclidean affine connection, which is presumed, we discussed taking the second order derivatives of the embedding, which is essentially taking the derivative of like the jth coordinate vector field on the manifold along the kth coordinate direction. And this is going to give you a second derivative of phi or var phi sub jk, which is like partial squared var phi over partial xj partial xk. And you can think of it as essentially in Euclidean space, it's just going to be the derivative of the vector field partial j um, um, in this larger ambient Euclidean space. So just the Euclidean notion of the derivative vector field. It's the derivative of partial j in the kth coordinate direction. So the image of the horizontal subspace in the basically the image of the line in the kth direction under the embedding. That's going to be a curve in the manifold. It's with respect to that curve that we're taking the derivative of the vector field partial sub j. Now, the point I wanted to emphasize here is that I mentioned that we then project this onto the tangent bundle manifold, and this gives us the covariant derivative, okay? So when we project onto the normal direction, or the normal bundle to the manifold, okay? So that's just the basically it's basically the smooth family of vector spaces, which is the orthogonal complement of the tangent space of the manifold at every point along the curve. So projecting onto that normal bundle, we end up with a new, projecting this phi sub jk, the second derivative, which is again a vector field along the curve, which is the image of the kth coordinate direction under the embedding map. When we project this phi jk onto the normal bundle, what we get is a component of what's called the second fundamental form. Okay, so how exactly is this form constructed? So it's a bilinear form, and it's, well, we've taken two vector fields, namely partial j and partial k. All right, we've taken two vector fields, partial j and partial k, and then from those vector fields, we have essentially taken the derivative of partial j in the direction partial k, and then projected it onto the normal bundle. And that gives us a new vector field. And it's a vector field not in the tangent bundle to the manifold, but in the tangent bundle, in actually the normal bundle to the manifold. So it belongs to the tangent bundle of the ambient space. Point is that if you then take the norm of that resulting vector, you get a bilinear form, okay? Because then, if you compose this with the norm, you're going to get a real number, so you get a function which eats in two vector fields, takes the derivative of one of the vector fields in the direction of the other vector field, then projects that onto the normal bundle, and then takes the norm of that